All right. Hello, we are LeTeam, and we are presenting the project Docking Port Detection in 3D Space. We are Neil, Nishanth, Pranav, and Jacob.
For our purpose, we seek to create an open source docking system that can be generalized for different spacecraft that would enable shuttles to dock to the ISS as well as to each other in space. We also want to aid in the flight process of these docking capsules and make it more public information for privatized companies as well as general federal companies to use.
Our dataset contains 10,000 images of the ISS and their respective docking port locations. Each picture has a label of the X and Y coordinates of the docking port, as well as the depth or distance from the ISS. This dataset was obtained as a part of an AI crowd challenge.
This is our model. We opted to build a multi-headed network in TensorFlow, building on the backbone of MobileNet v3 Small. We regressed 3 heads to regress the distance, X coordinate, and Y coordinate, and we made each head slightly different to deal with problems like overfitting and underfitting.
So speaking of these problems, we actually ran into a lot of them while making this project. We found a lot of different local minima, but we couldn't really find the global minima that easily. It would only minimize like 2 of the 3 heads at a time. The distance wouldn't regress, but the X and Y would. And there was also instances where our model would completely overfit and the validation loss would increase while the other loss wouldn't. And we also had an issue with how to visualize this, this 3D idea in a 2D space. So to combat these challenges, we were thinking through different solutions. We played around with different optimizers for the model. We looked into momentum-based optimizers. We also looked at dynamically weighted loss functions to try to help us escape these local minima. But what ended up working for us was actually tuning the learning rate and using a weighted sum for the loss function. That is what allowed us to train the model and overcome these challenges. And for visualization, we decided to have a moving camera in a 3D plot to help represent our 3D stuff in 2D space.
So this was the graph of our loss per epoch. This is the total loss. We opt to use mean absolute error because we're working with distance values. And this mean absolute error is the sum of the distance X and Y mean absolute errors. We see a really good exponential decay in the train and validation sets. We do see some slight overfitting at the end, but we combat that by using model checkpoint and early stopping. And at the bottom, we see a table of the train and test losses for the total distance X and Y. And we see that the losses are very close together, indicating that our model makes very good predictions and is generalized very well.
So in terms of visualization, on the left you see image number 420 from the dataset, and on the right you see a GIF animating what our model does. In this GIF, the shuttle starts at point 00, and we take the ISS and we place it on the true coordinates based off of the data that it was labeled with. And what you see here is a green line that maps the vector between our shuttle and the ISS. And as you can see, this line goes directly into the docking port, which shows you how strong our model is. It is able to accurately predict the docking port location for multiple of these different image IDs and accurately show us where the docking port is and how to get there.
For future directions, we were thinking about using polar coordinates instead of Cartesian because it allows us to have a more even distribution, especially along the x-axis. This would allow us to augment our data also and create a better spread in the X, and we could also include rotations in the ISS pictures and transforming the docking port locations. This movement would just help make our model more robust, and it would allow our model to predict more accurately with more spread out data.